This is nice. It's working really well. The hardware that we have right now, we've got our 3 LEDs run with 3 different current paths and a single switch that allows me to ramp up that intensity. All right, but as you might imagine, we want to make it better. If you're wondering how we got here, make sure you watch some of the previous videos and that'll walk us through how we actually developed the circuit, how we actually built it. So far, so good. But I don't want to be pushing buttons. I want this thing to ramp up its intensity automatically. Okay, this is where we get fun. So I did some searching online and I wanted to find out how I can do this. Because remember what's happening is I'm pushing this button. And if you remember, as I push this button from the previous episode, I talked about how we're turning a light on and off. And that green LED right here is that bedroom light, if you remember from the previous episode. And quickly turning that bedroom light on and off causes all of our neighbors over here to turn their lights on and off. And of course, we've connected those lights into these LEDs or bypass the switches so the LEDs change intensity. So the idea is all I need to do is figure out how I can automatically turn this light on and off. And so when I was searching online, I needed to find what we call a square wave generator, something that'll basically generate a pulse repeated up and down, up and down, up and down. And it turns out there's lots of ways to generate a square wave. I mean, you could use a 555 chip. You can use an op-amp, a 741 wired up a current way. But one of the coolest things that caught my eye, and I've never done it before, was that you can actually use a logic chip to create a square wave. And honestly, I didn't know you can do that. And so I was like, oh, this is pretty cool. You can actually use logic and a couple of resistors and capacitors to create a timing circuit, because that's really all it is. It's a timing circuit that will allow us to go up and down. Here's the schematic that I've come up with that will emulate the same circuit that I found online. So all it is basically, like you can see right here, I mean, there's got to be 2 resistors that help with our timing and a 1 microfarad capacitor that's going to allow us to time that pulse. This other 0.1 microfarad capacitor just serves as a bypass capacitor. Anyways, the parts that we have are right here. So I've got everything we need. This right here is the, well, this is the 51K, I believe. So that will be the 51K resistor. This one over here, I believe, should be the 15K resistor. I know you probably can't see it. I'm blocking it by the wires here. My apologies. And then here is our 1 microfarad capacitor, and we also have our 0.1 microfarad capacitor. So I'm going to go ahead and build it. What I'm going to do is I'm going to replace the circuitry I have for this switch and all of this debouncing and buffering mechanism I talked about in the last video. We're not going to need it anymore because we're going to automate the switch. I'm going to take this out and replace it with the circuit you see on the screen right now. Let's get to work. I think we have success. Take a look at this. I'm holding on to that reset button because remember, this button that you see my index finger on right over here, this is a reset that makes sure all the flip-flops are not flipping or flopping. So they're not moving. But I notice once I release it, then that initial switch that's turning on and off is going to be doing its thing. And watch what happens. I release this and all these lights start changing. Woo! Looks like it's working. This is awesome. I'm so happy. This is so cool. Okay, I wanna see this on the scope. There's our signal. So this is the light that's turning on and off. And it looks like what we got here, just looking down here, our frequency is 11.26 hertz. So that means that light is turning on and off just over 11 times per second. And that's why these things are changing at, well, the same frequency. So That's fantastic. This is the power, or this is the initial switch that's going up and down. This is really cool. You may have seen it earlier. I actually had the lights plugged in. They're not plugged in right now. That's why the LEDs are off. But if I plug them in, you should see some cool stuff happening. Let's try it. Look at that. It's working. It's going from 0 to high and then right back to 0. But it's doing that intensity change pretty quickly. I love it. And it's also blinding me, so I'm going to turn it off. I see green dots in my vision. Okay, so if you notice when it was actually changing like that, I noticed that we actually saw the very discrete changes in the intensity. So we saw that it would jump, from one intensity to the next. And I think what I'd like to do is I'd like to make that intensity a little bit smoother so you get more of a gradual change. And I think one of the ways we can do that, right now, we have 3 current paths. And those 3 current paths, if you remember from our previous video, that gives us 8 possible intensities. And I said that if we add yet just one more current path, add one more to make it 4, that will give us 16 possible intensities. So perhaps we can adjust this circuit to add another current path and make our transition more gradual so we can see less of those sharp changes. Let's do that. Here's the schematic that we have right now. And we can see that we have 3 current paths. 1, 2, 3. These are our LEDs over here, and these are the switches that are still in our circuit. But as we've just saw, we don't need these switches. In fact, these switches have been replaced by the outputs of flip-flops. So I've actually updated the circuit diagram, and I've removed these 3 switches and replaced them with flip-flop outputs. The other thing that I've also done is I've added another circuit path over here. And when I did that, I also noticed on closer inspection that these 3 resistors, these 3 over here, were actually unnecessary. I didn't even need them in this circuit because the reason they were there was to make sure that these MOSFETs get pulled down to 0 when these switches are not pressed. But it turned out that this contraption over here, all this circuitry, which is causing the purpose of this part over here, the circuit, is to ensure that when no buttons are pressed, the lights are completely off. So the fact that we had this is actually bringing these MOSFETs or the gates of those MOSFETs down to 0. So all of that to say that we didn't need these 3 resistors. So I took them out. Here's the updated circuit down here. So I've added a 4th current path. There it is. You can see it right over here. The switches are now gone, and in its place, I have an output from all these 4 flip-flops. And the flip-flops are being fed by our new clock pulse that we just generated using the 4007 chip. So this has been generated, and it's going to trickle down through all of the flip-flops and cause these MOSFETs to turn on and off. And what I'm going to do is, well, you're going to see this soon, but these diodes that are in our system, I'm just going to use the LEDs, the little indicator LEDs that I got in there anyways. They've served the same purpose. And so you see that those resistors are now gone. So I'm going to go ahead and I'm going to convert the circuit that we have now to this. And let's see what's going to happen. Oh, sorry. Wait. Before I go ahead and start converting, I can't believe I forgot this. When you add a fourth current path, well, that means we have to adjust these parachute resistors too. We can't forget to do that. Here's why. I have a little schematic here. Do you remember this? You may remember it if you watched the last video. This was that pattern that I had created to say that, hey, we're going from 0 milliamps to 350 milliamps, and I had 7 intensity changes to make it happen, and 3 switches. And so each switch controlled a current path. This was a 50 milliamp, 100 milliamp, and 200 milliamp current path. So if we add another switch, as you can see, some of my writing here suggests that I've added another switch. Really, it's just a flip-flop output, but it is another current path. Well, our diagram is going to change a little bit, and we're going to have a lot more options. We have 16 0 through 15 intensity changes now. And so the pattern changes. But remember, what's constant here is the minimum is 0, and the maximum, when all 4 current paths are enabled, I need this to be 350 milliamps. So I need to go from 0 to 350. And that changes things. If you look at the first 3-bit scenario here, we had a very nice 50 milliamp increase. 50, 100, 150, 200, and so on. Well, I can't keep the same 50 milliamp change because I'm going to reach 350 when I get to position 7. I need to get to 350 at position 15. So I need to change the step, right? The step of current needs to be lowered. In this case, it is. It's actually 23. And if you look over here, the current paths of each and every one of those, the required current through those 4 current paths are different. Before they were 50, 100, and 200. Now they're 23, 47, 93, and 187. You might be wondering, how the heck did I come up with those numbers? Okay, well, there is a secret. So on episode 11, I talked about this a little bit, and I also introduced a variation of a video that I did. We called it the hairy arms, where we actually dug into why this was happening. And in that video, I created this spreadsheet, which I'm going to bring up on the screen right now. I'm not going to spend time going through this spreadsheet on this video, but if you're interested as to how this spreadsheet was built, take a look at that hairy arms video, which I'll link in the description so you can actually watch, if you're interested, how this was built. If you're not interested in the theory behind it, we came up with this chart at the bottom over here. And this was our 15 intensity chart. And using this spreadsheet, I was able to figure out all of those different levels. That's where those current numbers are coming from. And we were able to figure out the individual current paths. The thing that's important for us right now is these 4 numbers. These 4 numbers are the resistor values, or the parachute resistances that I have to put into our circuit. So these, bring back the diagram or the schematic, these 4 resistors right now in our current hardware, they are not these numbers, and I need to change these 4 resistors to those numbers. So I'm going to do that while I adjust all of our circuitry. Here we go. I think we got it. There it is. I haven't plugged in the actual LEDs yet, so I don't know if it's going to work, but the sequence looks to be right. Watch what happens when I release the reset. I think that's the right sequence. My eyes don't work as fast as they should, but I think they're right. Let's try plugging it in and see what happens. Oh boy, here we go. I'm kind of scared. All right, let's try it. That is exactly what we want. This is awesome. We've got a nice gradual intensity. And I think, the way we can actually make the seam even more gradual is, well, A, we can speed it up a little bit, and we know how to do that. But more importantly, we have to add yet another current path. Actually, that would make sense because we'd actually have then 32 variations of brightness. Now, to put 32 variations here, in order for that to happen, we'd actually have to add yet another flip-flop. But you know what? What we've done here is we've stringed these flip-flops together, and we've created essentially a binary counter. There are dedicated chips out there that take a big string of flip-flops, put it together, and call it a binary counter, and deliver that package in a single chip. So on the next episode, we're going to explore using a binary counter with maybe 5 current paths to see if we can get a nice, beautiful, gradual intensity change. Until then.